So good afternoon. Welcome to the 29th Clinical School and Cambridge NIHR BRC Distinguished Lecture. It's a real highlight of our year. It has included some of the best talks that I have ever been to. I hope, George, that you'll live up to that. And on a rough calculation, the risk of winning a Nobel Prize after giving this talk is about 20%. So it's a great pleasure to introduce this year's speaker, George Davey Smith. I'm going to tell you a little bit about George. He is director of the MRC Integrative Epidemiology Unit in Bristol, and his research has really pioneered approaches to causal inference in population health. He's a clinical epidemiologist, and throughout his career, a particular feature has been promoting increased accessibility to data sets, and he's been at the forefront of doing this in the studies that he's led, including the Avon longitudinal study of parents and their children, ALSPAC, which has really been an extraordinarily successful study over time. He originally did a BA at Queen's College in Oxford before coming here to do the MB BChur at Jesus College here. And he must have spent some time in this lecture theatre. Exactly. Talking to one of your contemporaries who's here, he says that you were not a very studious medical student, George, and you didn't particularly like doctors. Anyway, he went on from there to do an MSc at the London School of Hygiene and Tropical Medicine in 1988, and then got his MD in Cambridge in 1991. He's had a very distinguished career. I'm not going to go through the numerous awards and prizes and markers of recognition that he's had, but I would like to mention that he was elected to the Royal Society in 2019. George, I'm really delighted and honoured to introduce you as our 2025 distinguished speaker to talk about evidence triangulation. George.
Thanks very much. That's very much sort of set up to fail, mentioning the Nobel Prize winners and the most entertaining talks. It's good to be back in Cambridge. I cycled past the restaurant opposite King's College, which I was sacked from as a dishwasher because I was caught eating and drinking the leftovers. I guess I can now say after all these years that they did try to throw me out. One of the surgeons here did want to have me thrown out of the medical school, but I managed to stay. So it's great to be invited back under these circumstances. So I'm going to talk about moving from correlations to causes. And I'm going to start just by saying why the approach that I'm going to discuss, why do we need it? Why not just use the approaches that the conventional approaches? And the basis of this in the variety of evidence thesis, I'm going to give varieties of examples of varieties of evidence, discuss the essential role of protocol development, pre-registration, potential limitations, and then there'll be a coda and advertisement at the end. So in terms of why triangulation, I think this picture would sum it up. Here, Trump's words, there's a tremendous amount of proof linking Tylenol to autism. I don't know if any people heard this. I listened to this whole press conference as I've worked on several studies of maternal paracetamol use and offspring outcomes. And I think we can fairly say that it was overstated, should we say.
And first, effective immediately, the FDA will be notifying physicians that the use of
I said, well, let's see how we say that. Acetaminophen. Acetaminophen. Is that okay?
So that was the highlight of the press conference for me, I have to say. Okay, but I'm now from Trump to another issue, which is nutritional epidemiology, and these are some studies that really had a big impact on what I did with my career. This was a paper that came out in the New England Journal of Medicine in 1993 that looked at vitamin E supplement use and coronary heart disease. So this was a large-scale observational epidemiological study which measured everything they could. They had a particular focus on diet, but they measured everything else they could. And the people who said that they took supplements, so the exposure is, having the jar, putting it in every night, taking a supplement. The people who took supplements containing vitamin E had about 35% lower risk of coronary heart disease. And you did the conventional epidemiological thing, which is, you adjusted for all the confounding factors that you'd measured, smoking, body mass index, etc., all the things that might influence the risk. And it remained, solidly below 1 and didn't shift much on those adjustments. And they replicated this. The same group had a second paper from another large cohort, which showed precisely the same thing. So we have these two back-to-back papers in the New England Journal of Medicine. And this got Clinton off the front page, off the front top story from the New York Times. Vitamin E greatly reduces risk of heart disease, studies suggest. Now, notice that language, greatly reduces. Reduces means you're actively doing something. It is a causal word. So it's unsurprising to know that, well, firstly, they also showed that you got the benefit really quickly. So, I mean, here you are. The people in those studies were nurses, and then there were men in a health professional study. There's large-scale studies of medical professionals. And they were shown that taking this stuff for a really relatively short period of time apparently led to this, rather large reduction in coronary heart disease risk. So they did what any sensible people would do, and they started taking it like crazy. So by 1998, these are the people in the studies. So by then nearly half of them were taking vitamin E in both studies, in both the male and female studies. And then you'll be unsurprised to know that randomized trials were done, large-scale randomized trials with follow-ups up to 13 years, absolutely no effect of vitamin E supplementation on coronary heart disease. And this is when the exposure measured in the study is precisely the same as what was tested in the trials. It was taking vitamin E supplements. They're clever folks, so they stopped taking the vitamin E supplements once the trial results came out. But it's not totally harmless if people are doing one thing. If they think they're doing something that's reducing your risk of coronary heart disease by 35%, you might think you might not have to do certain other things. Anyway, when these results were first published, it wasn't in the New England Journal of Medicine. It was in a talk of which there was a published abstract. And in the published abstract, the team showed also that beta-carotene consumption, this wasn't supplement use, it was consumption, was related to lower risks of coronary heart disease. And this a brilliant paper by Richard Peter, really, it's a very good paper. It's a sort of proto-triangulation of evidence exercise where they looked at data from human studies, they looked at animal study data, they looked at cellular studies. They also had a natural experiment in Brazil where some places the oils contained large amounts of beta-carotene. The evidence looked really, really pretty good. And this was for reducing cancer rates. So here you had something which appeared to reduce both. It's the only time in Nature that I've seen a note by the editor cautioning unwary readers not to start eating large quantities of carrots on the basis of this paper. And so the publicity around the publication of the abstract led to a little turn up in beta-carotene use by both of the study subjects, up to just 15%. But you notice that started falling really quite quickly. And that started falling because the first large-scale randomized trial came out in 1994, which you'll imagine, as you might imagine, did not show any reductions in cancer, if anything, adverse, and no reductions in coronary heart disease. And Richard Peto led one of the trials, the second trial that appeared. So people stopped taking beta carotene. Now that's two stories. Vitamin E, beta carotene. This played out again and again and again. And this was when I was training in epidemiology, thinking this was a career to go into. Retinol, vitamin E, we've talked about. HDL cholesterol, good cholesterol. There'll be those of you who'll be able to remember when HDL cholesterol was considered good cholesterol. He wanted to raise it. Alcohol raised it, so that was a good thing about drinking alcohol. Randomized trials, well, Mendelian randomization studies and randomized trials completely flat, suggested no causal effects of HDL cholesterol. It's not protective, raising it. Hormone replacement therapy was supposed to protect against coronary heart disease. In trials, if anything, the other direction. Vitamin C, folate, selenium, and prostate cancer. All of these large-scale randomized trials were done on the basis of the epidemiological evidence. And this was the best evidence. People aren't going to go ahead and spend huge amounts of money on doing randomized trials of things which aren't the best candidates for randomized trials. Vitamin D also, large numbers of randomized trials showing no benefit. And there's many others. So this is really disheartening because this is doing what we were taught to do. Cohort studies were the top of the tree of epidemiological studies, where you measured everything, you could statistically adjust for it with the misleading term. People say, I controlled for this variable, which makes it sound as though you really are fully taking it into account. And all the dietary stuff still carries on appearing. And some of you might have known this controversy about the red meat question and the large-scale reviews from Ottawa that said that the actual evidence, when you put all the evidence together, was very weak. And the people who led the vitamin E studies and the beta carotene studies, etc., they now say that randomized trials aren't the appropriate way of testing these things. They don't like they shoot the messenger. This is a great article by Rita Rubin, very well worth reading, about what one learns about health. So that's just saying, why do we need triangulation? Why not just do the best studies you can do? And you can't go straight to randomized controlled trials for everything. They're very, very, very expensive. So an issue is that the volume of data from studies which have the same biases doesn't help. We all hear about replication. With the vitamin E studies things, they replicated it in the same issue of the New England Journal of Medicine. If you're studying something in similar contexts where the health conscious are taking the vitamin E supplements, you cannot statistically adjust for those differences between those groups. Or when you have reverse causation, which is actually leading to something being raised, you can't take into account the developing disease processes. So just simply replicating things with the same study designs stops being useful. I mean, here's the beta carotene. Those are all the cohort studies. Matthias Egger and I did this meta-analysis 5 years ago. But the studies that were available up till then all showed, apparent protective effects of beta carotene against coronary heart disease, and the trial showing the opposite. So just getting more and more and more of these observational studies would have been utterly useless. In fact, it becomes counterproductive because you get more certain about a finding which is wrong. And also, of course, there's degrees of freedom that the analysts have. I'm not going to go into the details of what the hypothesis are looking at, but this is a really lovely study from the sociological field where the investigators provided 73 different groups of analysts with exactly the same data set, told them the hypothesis they wanted them to examine, and then they were to write a report of what approach they used, and then come up with their findings. Now, what they then found is in the reports, a quarter of them showed effects in one direction that were statistically significant. You're not allowed to use the term statistically significant in Bristol. We've banned statistical significance 25 years ago, but sadly, people still use it, so it's used here. But the remarkable thing is 17% of them got a statistically significant result in the opposite direction. Of course, everyone wants to find something that's statistically significant, and less than 2/3 had estimates that overlap the null. So that's just analysts with exactly the same data set, just fitting different models, can lead to that to this difference in the findings. There's so many degrees of freedom when people analyze data, and of course, people want to find things that are striking. So what's important is not the volume of the data, but it's the variety of the evidence. And what this means is using different methods that will all be biased. All methods have biases, or it can be distorted, including randomized controlled trials. But where those biases in one method would not relate to the biases in the other method. So you've got to reason about why one method won't have the same biases. And I'm going to come back to this point. It's easier to talk about when you actually consider the different methods that can be used. And then you've got to defend the fact that you think the biases in one approach won't bias the other approaches. And mechanistic reasoning is also can also be important for establishing causality. I'll finish on that. So examples of varieties of evidence in etiological epidemiology. Well, I've talked about conventional observational studies, and the assumptions in conventional observational studies that allow you to say you could recover causal estimates is that there is no unmeasured confounding. This means there's not a single factor that might be i.e. influencing both your exposure and your outcome be a confounder. There's not one, and there's no measurement error. You've measured every single confounder absolutely perfectly. And that equation means you're not looking at epidemiological data, because that's just simply not possible in any epidemiological data set. And there's many flavors of observational studies, calling them real world evidence or target trials, or these terms you often heard. NICE now allow real world evidence to be entered. It doesn't make them any more evidential. They suffer from the same problems. However they're dealing with it, there's no way around the no unmeasured confounding, no measurement error. And here's a pair of papers showing the target trial. This is a target trial real world evidence approach. This study appeared in the Lancet. It was called Senior and STEMI. And what it did is it used electronic health records data to try and estimate the effects of interventional cardiology in people who had non-ST elevation myocardial infarction. So they tried to mock up a trial from the observational data. They did it in all these ways, the advanced approaches, and they predicted 5-year mortality of the intervention was 0.68. So a really large interventional effect. And they said that in the absence of a trial, then this was the best evidence there was. They called it Senior and STEMI because there was a trial called Senior Rita, which was occurring of precisely the intervention that they were looking at in the target trial. That appeared in the New England Journal of Medicine, and no benefit. So they have two. These are the approaches that you'll hear when people talk about real world evidence, target trials, etc. They can't avoid the problems of unknown confounders and measurement error. Okay, so what things can one do? Well, one is to think, if confounding is the issue, then if you can get contexts where the confounding is different, the confounding pattern is different, then in those contexts, the results, your findings won't be distorted in the same direction. No, so an example of this would be breastfeeding. So Patrick mentioned the Avon longitudinal study of parents and children, and one of the great, a lot of work has been done in ALSPAC on what happened to the kids who are breastfed. And the bottom line is that breastfeeding was associated with everything good. you know, lower obesity rates in the kids, you know, lower allergic disease in the kids, but, you know, doing better at school. We looked at like the Christmas presents they got, and the kids who were breastfed, they got better Christmas presents. You know, that was as you might imagine, because of course it was families with greater better material circumstances, with better parental education, etc., were much more likely to breastfeed. We have to admit, we were involved in meta-analyses that did look at all these, put together lots of studies from lots of places, but they were virtually all in high-income countries. So Mary Jo Brian, who went to Pelotas in southern Brazil, and in Alsbach, you know, you had massive socioeconomic confounding of breastfeeding, as I just showed, and in Pelotas there wasn't. So here you went to a place where the better off people weren't breastfeeding more. And if you looked at all the socioeconomic indicators, massively different, starkly different. So there you will think, well, you wouldn't expect to see the same associations if they are generated by confounding. And what Mary Jo found was that in Alsbach, where there's strong social patterning, as I said, being breastfed meant you had lower blood pressure, the kids had lower blood pressure, they had lower body mass index, and they had higher IQ. In Pelotas, where there was very weak social patterning, the results were starkly different. In particular, you know, in relation to BMI, if anything, it was in the other direction, except for IQ. And if you got all the lower and middle income country cohorts together, you got really precise estimates in the different direction to Alsbach with statistical evidence of a difference. But unfortunately, Pelotas was the only one that had done a sort of IQ measure. And then with Richard Martin from Bristol, set up a follow-up with the originators of the study of the only randomized trial of breastfeeding there is, which was in Belarus, which had the lowest breastfeeding rates at the time. The trial was set up by Mike Kramer from Montreal. And Mike set this trial up with 36 hospitals, and half of the hospitals, it was cluster randomized trial, half of the hospitals promoted breastfeeding, half of them just did normal care. And at 3 months, you got that only 4% of the usual care kids were being breastfed, and 40% of those in the hospitals that promoted breastfeeding. And then Richard and co did a long-term follow-up. So there's randomized controlled trial data on these outcomes. And breastfeeding had no influence on blood pressure or body mass index in the randomized trials, but it did have an effect on cognitive ability. So you see that was the one outcome which showed the same direction of association in Alsbach and Pelotas. And the Pelotas group says our Victoria have gone on to do a lot more work on this. So that's an example of cross-context comparisons. You just go to a different context where the confounding structure is different, and the confounding structure might be different in time. You know, if you don't need to go to different places, you might be able to do the study in the same place when the context was different, when the confounding was different, especially like socioeconomic confounding. So we all know that if you're eating fried food, you die. And this was available. Women's Health Initiative in the US, you know, relatively recent paper showing more fried food, higher mortality from cardiovascular disease, and surprisingly from nearly everything. But anyway, that's what you see. So when the first large-scale prospective study of smoking was set up in the US, they collected vast amounts of data, and you could pay. Those are the days where you could send money and you could get the supplement of all the analyses that they did of the study that set up in the late 50s, Hammond and Horn study. And I paid for this, and you get this wonderful result. They had they looked at every factor you can imagine. So this is fried food. And then the mortality, death rates amongst never smokers and smokers. Look at the gradient. If you had none, if you had no fried food a week, you had very high mortality, and it just carried on declining until you had 15 or more That's not just breakfast and dinner. You had to have at least one fried lunch as well. And of course, in this time, fried food was state. Better off people were eating more fried food, and you got the exact opposite results. So I think this does make one think a little bit about when one reads these things. That's what that commentary I showed about dark chocolate. It's always things that poor people do that are supposed to increase mortality. Like dark chocolate is good for you. Yeah, great, thank you. That was a serious paper. Anyway. So cross-context comparisons, and hopefully that you now get this notion. I say, well, the biases would be orthogonal. The biases are different in the different contexts. You deliberately choose the contexts with the different directions of confounding. Okay, so negative controls when you can use a negative control outcome when you look at an exposure and it relates to something, and like vitamin E related to coronary heart disease. And so many of the papers, even 40 years on, they still do this. They just publish one outcome. If you see all the outcomes, then that might make you suspicious if you see the outcomes that are just not plausibly related to the exposure. And now there was one stage, a big story about smoking and suicide. And that smokers had higher rates of suicide, and the mechanism was serotonin, etc. This was advanced, and I had the fortune to spend some time in Minneapolis analysing the multiple risk factor intervention trial data. They'd screened 1/3 men. This was by far the biggest study anywhere in the world, which is why I went to Minneapolis to be involved in analysis. We showed the smoking and suicide association, but it's smokers. Smoking might be partly self-medication for depression, for example. And if you're depressed, you're going to find it rather difficult to give up smoking. So there could obviously be a lot of reverse causation and a lot of confounding involved in that. So this being the US, there was the perfect negative control outcome, which even the most virulent anti-smoker. I am virulently anti-smoking, by the way, just to make sure you've got that on record. The most virulent person couldn't say was plausible, and that was being murdered. And sure enough, smoking increased your risk of being murdered. Now, the only plausible explanation for that is the paramilitary wing of the health promotion agencies are going around literally shooting smokers as the ultimate deterrent. And I discovered after that that the wonderful Diana Petiti had done precisely the same in a letter in the New England Journal of Medicine, looking at hormone replacement therapy and mortality. And this was when the study that brought you vitamin E and is protective, and et cetera, et cetera. That same study was suggesting that hormone replacement therapy, observationally, but controlling for everything, was protective. Diana Petiti showed that observationally, hormone replacement therapy was as protective of deaths from accidents and violence as it was from cardiovascular disease, which would make one somewhat suspicious. And of course, the latest thing is ultra-processed food. The ultra-processed food is the thing poor people do, and it's terrible. It causes everything, apparently. It also is observationally associated with increased death from accidents and violence. You do adjustment, you adjust for everything, and it remains just like the associations with whatever condition it is that people are writing about. So those are negative control outcomes, and I think they really should be widely used. I mean, journals shouldn't take papers unless people report multiple outcomes, so you can see the plausibility of what's been promoted. So you can also have negative control exposures, and working on ALSPAC, a very obvious one is looking at the effects of cigarette smoking, because again, maternal smoking relates to everything bad, like breastfeeding, but you have the obvious negative control, which is a negative control in the exposure sense would be something related to the same confounding factors. The obvious one is the dad's smoking. So if you're thinking about an intrauterine effect of the mother's smoking, the dad's smoking isn't going to have an intrauterine effect in the same way, obviously. And so here you have a positive control. Positive control should also be used when they're available. We know that smoking, we really do know that smoking reduces birth weight of the offspring, and the mother smoking is associated with reduced birth weight of offspring, and the father smoking, especially when you take into account the assortative mating by smoking with an adjustment, just isn't related to the low birth weight of the offspring. So that's what a cause looks like. There was also a lot of promotion of the notion that maternal smoking also made the kids fat, just like not being breastfed made the kids fat, etc. And the dad smoking related pretty similarly to the mum smoking. So we're suggesting that it's a family-based sort of socioeconomic factors that are going on. It is not the effects of the intrauterine effects of smoking. If it were, the findings would look like the ones on the left with birth weight of offspring. I haven't got time to present every sort of approach, but there's within sibship studies can be very powerful for certain issues, like with maternal paracetamol use, which is where in the between sibling studies you did not see this association between maternal paracetamol use and neurodevelopmental outcomes in two large studies, Scandinavian studies. Because when you look within sibships between siblings, you are taking into account family-based factors that might be driving the effects. There's regression discontinuity design. Regression discontinuity is when you can say, something happens at a particular point which changes the treatment people get. For example, treatment. I'm going to show a treatment example, but you can use it for many, many other things, like amount of education, which I'll come on to that actually. And there's a nice one with age and coronary artery bypass grafts and mortality, when the US guidelines basically say 80. At the age, up to 80, you're much more aggressive about actually just grafting, as the person soon, etc. And here, and so this is a great study. What it looked at is people who were like 2 weeks before or 2 weeks after 80, and what they showed 2 weeks after the birthday. Look what we're just getting lower rates of grafting, and they're only 2 weeks older or 4 weeks older at the most, and yet there's a lower rate of grafting just been seen there. So this shows that the regression discontinuity is doing something. And then this shows that it translates into the outcome. So that if you were the more, when you were said you were 2 weeks before, then you were more likely to get grafts in 2 weeks after, and the grafting was sort of good for you. And so the answer there is that I'm probably about the only person here old enough, is approaching the age where get admitted in the US, but just remember to say you're 79. You're 79 forever when you go into A&E in the US. So then there's Mendelian randomization, which I've spent an inordinate amount of my life on. I can't explain it briefly in a talk, so I'm going to play a 2-minute video. Hopefully.
Epidemiologists are interested in understanding factors related to health and disease. Do smokers tend to die younger than non-smokers? It certainly looks that way. But disentangling cause and effect can be difficult. Smokers are different on average from non-smokers. They're more likely to drink heavily and have less healthy diets. But even if we measure these confounding factors, we may not measure them perfectly, or there may be others we haven't measured. Also, as people become ill, they may cut down or give up smoking, which could wrongly suggest that reduced smoking leads to worse health. We could randomly assign 50,000 people to smoke and 50,000 people to not smoke and follow them up to monitor their health. This removes the possibility that any other factor could be responsible for any differences we see in their long-term health. But this is neither ethical nor practical. Fortunately, we've all been recruited into an experiment without knowing it at the point at which we were conceived. Our genes, which are passed on randomly from generation to generation, influence how much we eat, sleep, drink, smoke and more. These genetic influences are not affected by anything else you may or may not choose to do in your life. They're not related to confounding factors. We can use this knowledge to learn about cause and effect, grouping people according to their genetic code. This method is called Mendelian randomization. For example, smokers who carry one version of a gene called CHRNA5 tend to smoke less heavily than those who carry a different version. When we group people according to which version of this gene they have, we find that the people with the version of the gene associated with heavier smoking do indeed die younger. But is the gene influencing how long we live in some other way? We don't think so. When we look at the same gene in non-smokers, there's no effect on life expectancy. So the effect must be driven by smoking. Using this method, we can show that smoking causes lung cancer, heart and respiratory disease, and many other diseases, but does not seem to influence depression or anxiety. Mendelian randomization has already begun to tell us about factors that influence our risk of disease. Now we're using the same approach in other ways, to look at several risk factors together, and to look at what influences disease progression, which may help us to develop new treatments.
So when you go home, get your kids to watch that, and every time you're on a new IP address, watch it again. Because my aim for my post-retirement career is just with YouTube millionaire, and this is the only YouTube video I've ever made which has had large numbers of views. So please watch it again. Anyway, and so that was so you've all got Mendelian randomization now, and this has been an example, some lovely work. Steve Burgess from here led quite a lot of years ago now, put together a consortium to analyze the relationship between C-reactive protein and coronary heart disease. At the time, C-reactive, well, actually, in the early part of the 20th century, C-reactive protein was being referred to as the new cholesterol because people thought it was strongly related to coronary heart disease rates. Drug companies were developing CRP inhibitors. But the thing is, atherosclerosis is an inflammatory process, and so it puts up your CRP. And basically, everything bad puts up your CRP, as we'll show. But if you look at it observationally, there really is a really strong effect. And if you adjust for all the confounders, and I'll show you the confounders adjusted for, that effect did go down a little bit, but remained, highly statistically robust and quite unsubstantial. So here are the confounders. And related to CRP, and what you see is this is just related to the CRP, circulating levels of CRP, and you see that as what I say is true, everything bad relates to higher CRP, like smoking, low social class, higher body mass index, higher bad cholesterol, etc. All of the higher BMI particularly, all of them relate to higher CRP. But showing that Mendelian randomization in this situation does what it says on the tin. If you look at those, you look at the genetic variant, this is a promoter region variant, which is related, a cis variant related to higher CRP. The variant is just not related to any of the confounders. So the method is here doing what it says on the tin. And therefore, if you get two groups of people just categorized by the variant they carry, it's like a sort of randomized trial. You've got one group, the average CRP in the group with one version of the variant will be lower than the average CRP in the other group. I mean, at an individual level, it's a very poor predictor, but at a group level, it works perfectly. And what one sees is that in the Mendelian randomization analyses for coronary heart disease, absolutely not. And some earlier MR studies, and then the drug companies stopped developing CRP inhibitors, and they never went to trial. But the thing I want you to see from here is this is what a null result looks like. 1.49, adjusting for all the confounders, goes down to 1.33, and that's the only thing that people report in the abstract, the multiply adjusted thing. That is what null associations look like. They all look like that. So just think, next time when you see the headlines of papers showing that this dietary factor relates to it, just think of this, that's a null result. That's what a null result looks like. You can do MR in both directions, which can be really valuable because it can tell you about the confounders. So this was done very early, but again in the days, by Nick Timpson, who was involved in the identification of FTO as the first genetic variant, common variant to be found, to be related to difference in body mass index. So just using FTO as an instrument for BMI, you showed that BMI does indeed increase CRP. So this shows partly why CRP is predictive, because BMI drives it up, and BMI causes many things. But if you do it the other way around, but FTO associates with CRP, as I say, that's what that showed. But if you do it the other way around, CRP has no effect on, no association or effect on BMI. So the fundamental assumption of Mendelian randomization is gene-environment equivalence, and that is that if your perturbation is through a genetic change, then the perturbation in the phenotype will have the same downstream effect as if it's through an environmental modification. And in monogenic disorders, there's many examples of this. For example, pellagra niacin deficiency. It's the genocopy of that is Hartnup disease, which is a mutation which leads to poor absorption of tryptophan, which is converted to niacin and produces very similar symptomatology. So you get the same outcomes. But that requires sort of justifying in all situations that it is reasonable to think that. I mean, I give some quotes from developmental geneticists like Mary Jane West, Eberhardt, etc., where this is conventional thought, gene-environment equivalence in developmental genetics, for example, the gene-environment exchangeability. So you need to justify that and relate it to the biological processes. So if you consider CRP as the phenotype, then a cis variant, promoter region variant in the CRP gene, which relates to higher levels of CRP, would seem to be a reasonable mimic of reducing your CRP level with a monoclonal antibody or whatever. But FTO would not be a good indicator of CRP, even though it's the fourth strongest genetic variant association with CRP is FTO, because FTO influences CRP through body mass index, and it's not going to produce the same effects as just changing CRP levels. Nor would genetic variant related to smoking heavier that was in the video, or anonymous trans variants are unlikely to be. So it's got to be very careful. That's why this mass number of terrible Mendelian randomization papers that any of you who are medical journal editors will know about come from the abilities to mine data in mindless fashion. An example of where gene-environment equivalence is absolutely directly obvious is when you have a genetic variant that relates to a phenotype, and that genetic variant is actually targeted by a drug. So HMG-CoA reductase, the gene, there are genetic variants around HMG-CoA reductase that relate to different levels of cholesterol, and statins target HMG-CoA reductase. They're doing, so there's obvious gene-environment equivalence. And then we have the same for PCSK9 inhibitors, PCSK9, Niemann-Pick C1-like-1, which is involved with cholesterol uptake by the gut and is mimicked by ezetimibe, etc. And they map beautifully together. That if you look at the data from the randomized trials for 5 years in the genetic studies, but the genetic studies predict a much larger effect and of course you'd absolutely imagine this because the trials are just 5 years of 5-year difference in cholesterol in the two groups. The genetic variants are related to a lifetime difference. And, when they autopsied Korean soldiers American soldiers in Korea, they're getting atherosclerosis at 18 or 20. So of course you would expect the genetic effects relate to a lifetime effect, but they are equivalent in terms of the downstream effect. But it's just that the genetic effects last for life. You can use genetics to estimate confounding, like to say why are you getting these observations. So I talked about HDL, so-called good cholesterol. Well, one reason for the HDL associations with everything good, like lower rates of coronary heart disease and lower risk of sepsis, is that IL-6 drives CRP, and drug trials targeting IL-6 do show benefit for coronary heart disease and sepsis. You can have non-genetic IVs. So there's other things that policy changes, for example. When one state in the US increases the tax on cigarette smoking and then the neighbouring states haven't done so, it's like the regression discontinuity. You can say, you can then look to see what happens to birth weight of offspring occurring over that period where there's going to be a differential effect on smoking, and randomised controlled trials, of course. So, an example of triangulation would be maternal smoking and birth weight of offspring that I've already mentioned. And in this, every study design shows the same thing. Conventional observational studies, cross-context comparisons, looking in poor countries, rich countries. Negative control studies, I've shown that within SIBSHIP, Mendelian randomization, non-genetic IVs, the tax example. randomized controlled trials. And here, and what I want to say here is that in each particular question, there might be different designs might come into place. What I've talked about is just a sample of the sorts of designs that can be used, because for maternal smoking birth weight of offspring, a great design are the children of discordant monozygotic twins. If you have a pair of monozygotic twin sisters and one of them smokes and one of them doesn't, they're matched for lots of other things. And you see the difference in birth weight of offspring by smoking. So the important thing is that the direction and magnitude of biases in the studies are different, as I said. This can be formalized and has been done so by Paul Rosenbaum and co. To say that there's no causal effect on the exposure. So imagine that net of the causal effect of the exposure, if there is no causal effect of the exposure, the results from the different study designs the results of one design would not predict the results of the other design. Now, the problem with this is you need a large multiple study designs, and you need multiple studies using each design. But you could test it with formal mediation analysis, but there aren't any examples really with enough. There aren't any examples that I know of with enough data to do that. But this notion of independence of biases could, in principle, be examined. Then, how do you put the evidence together? Well, firstly, you have to think, what are the different studies actually trying to estimate? What is the target of their estimation? And can you scale them? And sometimes between different designs, you can scale them. So going back to this, between our randomized controlled trials and Mendelian randomization, they scale very well. 5 years of treatment gets you about 35 to 40% of what you see in the genetic studies. And then in principle, you could scale them and combine them. And remarkably, even in the same data set, you can get two estimates and combine them, as Rosenbaum's written about, if the biases are truly independent. You can use UK Biobank twice if they randomized people in the UK Biobank. I've got an example of doing that. So one can do one can do formal evidence synthesis. Now, combining RCTs and Mendelian randomization is very powerful, and there's a review of when this is possible to look at RCTs and Mendelian randomization studies together. You can also combine methods that would lead to discounting of flawed evidence. So here I'm going to talk about Mendelian randomization and negative controls. And this is the situation of vitamin D. I told you all the randomized trials of vitamin D have been null, but the observational studies always suggest a really substantial benefit of higher vitamin D. And this is the relationship to all-cause mortality. This is a relationship between different causes of mortality. Now, here you've basically got sort of negative control there. I think whenever you see anything which just relates in the same way to everything, non-cardiac CVD cancer mortality would include, accidental and violent deaths. It does make you think that biology doesn't usually sort of work like that. But that's the observational associations in this paper. And then they used the Mendelian randomization method, which supposedly allowed for nonlinear estimation, and said that the stratified Mendelian randomization suggests that there's benefit for people at the lower end of the vitamin D group, and their findings have implications for the trials of design of vitamin D supplementation trials and potential disease progression prevention strategies. And this was if you put your head sideways, what you see is exactly what you see in this curve is precisely what you see in the observational curves. These results the Mendelian randomization results just reproduce the same as you saw observationally, and remarkably, the overall estimate is 0.99, but in every strata, there's benefit. So overall, you get no benefit, but in every strata, you see benefit. Does that work? Now, this is where people think that you have this vague memory that someone somewhere has told you about Simpson's paradox, and apparently you can get things like this. You cannot get things like this with Simpson's paradox when the effects are causal and the distribution of the data and the assumptions of MR hold. So this is literally impossible. This means that something is seriously wrong with the approach. And this is so we just Gus Hamilton just analysed using precisely the same analytical approach as was used for cardiovascular disease, etc., but looked about whether vitamin D changed your chromosomal sex, and yeah, vitamin D appeared to actually change your chromosomal sex, and low vitamin D deficiency makes you more older, makes you more male and older. Now that's not possible. So that's the use of a negative control where it's very clear, and the paper was retracted, and the commentary that went with the paper was retracted, and the redone analyses which came out. The paper was then reprinted with different analyses and said no effect. So and there's a great systematic review of those, and it's interesting. These things are interesting because actually working out why you just simply replicate observational findings with this method has been really interesting for us, and we've got for us it's helped develop a way of analysing antibody data. So you never know what you're gonna find out by trying to unpick why things get the wrong answers. Or regression, MR and regression discontinuity. This is using in UK Biobank. It spread the time when there was a change in the age at minimal school leaving, which occurred, and then the people who couldn't leave school at 15 had to stay on to 16. So it led to about half a year longer schooling for the people who followed that single year change to those that didn't. And so you can use that to estimate the effects of schooling on health outcomes, and you can use Mendelian randomization, and the findings of the two approaches are really pretty congruent. So, combining estimates depends on whether you think the estimates are combinable and the assumptions you're willing to make. And this is one of the sort of two areas that are most in development. I think require most development in triangulation. I'll get back to the other one, but I'm not going to go into the technical details of this. And there's a paper with an example of beta carotene, which I could give anyone the reference to who's interested in that. I think most interestingly and most importantly, really, is what do you do with evidence that doesn't just give you an estimand? There's lots of evidence which should help us decide whether something is a cause or not. And a lot of it isn't something that in a human study can give you an odds ratio of 1.24 or whatever with confidence intervals. It's mice studies or cell system studies, etc. It's a different category of evidence, and but there's limits to the conventional biologically plausibility, because in the discussion of papers they always say we find this and this is biologically plausible, and they'll then give some references to show how it's biologically plausible. Now I've worked on HIV and AIDS and STD prevention for quite a long time. I used to read all the magazines, all the journals, and at the School of Hygiene Library I found this paper about male to female transmission of HIV, and it was looking at the effects of oral contraceptives, and this one found that oral contraceptive use was associated with a greater transmission, male to female transmission, and they said, well, yeah, but it's immunosuppressive, and it has a direct effect on the genital mucosa. Gave references to it, and I thought, yeah, that sounds plausible. And then, literally the same month, another paper had come out in a different context, and in this study, they found the reverse. They found that oral contraceptive it was protective, and they found a reference that said that it increases thickens the cervical mucus, and that acts as a barrier. It's an incredibly low barrier finding, and this was before ChatGPT, when you can just put in find study that shows, and it'll give you a load of partly made up references. But so we can't just use biological plausibility. But so to me, this is the real major issue with triangulation, is thinking of ways of which you can actually integrate in a principled manner, integrate such evidence, which is really such evidence about causal questions. In climate science, for example, they've been developing methods where they elicit expert advice, and they choose groups that are supposedly representative of different views, and then get their priors on different things and actually use those priors. But there needs to be a lot more. There needs to be more work in this area, and it really would be important. Those of you with any epidemiology training will probably notice that a lot of in triangulation resonates with Bradford Hill's viewpoints about causality. And I'm going to finish with a crossword analogy about how one could think about triangulation, about how one could think about the scaffolding of evidence, and also just to see if anyone's awake here. So this is a Guardian cross. It's the quick crossword. It's the easy one. So you're thinking about convoluted, and you get about 6 possible answers to convoluted. So you can't put one in for convoluted. But then you see, this is a medical audience, so you should get this one. A and O, for instance. 5 and 5, what could that be? Sorry? Blood groups. Yay, there we go. So that's right. So we're pretty sure about that. And then gangster's girlfriend, 4 letters. Mole, yeah, so we're pretty confident about that. There's one person here. The next one is Besom. Patrick Chinnery should know this because this is the word. Yeah, there we go. Very good. Northeast. It's not. Yeah, you don't get Besoms in Warrington, mate. We got a lot of any talk of that. So yeah, so you get Broom, and that gets it down to confused or tortuous, and then you get discharge of water, which is outflow, and that means tortuous becomes the answer, and the others. Now the reason I think the scaffolding helps is that data which doesn't actually directly intersect with your question can help build the scaffold which makes your answer to that question more plausible. Or so imagine the studies on looking at methods and showing that the method is completely unreliable. Then that takes away part of that scaffolding. So if studies using the same method but on a different question get clearly wrong answers, you don't want to trust that method for your question. So it's the fact that things which are it's the intersection of many of the things which actually stabilize inference. It isn't just the direct answers to the questions. It's how the methods are developed, demonstrated to be real. It's about how maybe mediating factors have been shown to influence outcomes, etc. So it's a sort of scaffolding rather than simple lines. And the output of triangulation exercise, I think, should often be to say which bit of evidence would really move us forward on this question. It's not worth just replicating things. What things are actually missing that we went out and got those data would allow us to answer it. And you've got to communicate the evidence highlighting existing uncertainties, which we obviously didn't see in the press conference. I think it's very important to actually register a protocol for triangulation exercise, because otherwise you can sort of check, not deliberately, but often if you're testing a hypothesis, you have some investment in the area, and so one can subconsciously be drawn to evidence which points in support of what you believe. And this was shown when pre-registration was brought in by the National Heart, Lung and Blood Institute. Before this, people could just do a trial and never report any results. After it, they had to report the results. And suddenly, studies with heart, you can see there was a quite big difference in the actual degree of positivity of findings after that time. And registering a protocol would also stop people doing the p-hacking. That's doing those analyses, like I said right at the beginning, with the sociological example, just to get significant results, or hypothesizing after the results are known. It's all, as we said about biological plausibility, it's very easy to come up with a hypothesis once you've seen the results. And I sort of thought that anyway, sort of thing. And then you think, I don't think, as I say, it's not machinations, but it's cognitive biases that all scientists have. You have to have open access to data so that people can actually try to replicate your results. And those 2 vitamin E studies that I said did influence my life, I won't go into this, and that terrible period with epidemiology. This led me to write an editorial for the BMJ about increasing the accessibility of data see for yourself should be watchword, because I tried to see whether I could get access to the data. It was very clear that I had no possibility of getting access to the data. It was their data, and they weren't going to let some guy come along and to see whether it related to accidents and violence. So access to data is absolutely key. And I went back to look at this. It's lovely to realise I was saying that the papers submitted to journals had to be accompanied by a disk copy of the data. Isn't that wonderful to think about? Disks they could be sent to the statistical referees. But with journals being completely flooded by many too many papers, this will be a way of actually leading to a fall in submissions. The editor of the BMJ took my proposal to the editorial board. He supported it. He was the only vote in favour of actually introducing it. So it didn't get it got introduced years later. All code should be open. The detailed protocols should be registered, and the consensus relates to what evidence are admissible, not the findings. That's the important thing. If you get a protocol group who have different views on a subject, and that's what you'd want, then you decide what evidence would be considered admissible, and then you debate that rather than debating the results of studies that are available, which is never particularly useful. You could game the system, you could pre-register after the results are known, but that is fraud. So if you do that, then you are actually doing fraudulent work, and there'll be other limitations, I'm sure. And there's the CODA. The CODA is Trump's executive order on restoring gold standard science. And the thing about this is, it's supposedly his words. Weighted scientific evidence means an approach to scientific evaluation in which each piece of relevant information is considered based on its quality and relevance, and then transparently integrated with other relevant information to inform the scientific evaluation. Yeah. So, what is interesting is the actual documentation. The NIH is sort of supporting triangulation. They say we should emphasise uncertainty. Getting null results should not be seen as a failure. Null results are important, etc., etc. They say all that, and the action is the action that we've seen. So I'd just like to acknowledge people who did the work. And then just, Christmas is not that far away. And if there's anyone that who you basically don't like very much, but you've got to buy them a present, can I recommend this book? This is the ideal present for someone you don't like. And I'm happy to sign copies if anyone. But if anyone's interested just in a gentle introduction to triangulation, then that's out a few weeks ago as a review. Thanks very much.
Thank you, George. We promised everybody that we'd be giving them lots to think about, and that certainly has given everybody lots to think about. I'm absolutely sure of that. So questions, please, for George. With the microphone going round at the back. Patrick here at the front.
Just making you get some exercise.
Yes.
The next one is going to be right at the back. I'm going to.
So, George, I worry that the publication of observational epidemiological studies has contributed to the general public scepticism about scientists. I'd be interested in your thoughts of that view.
Yeah, no, I agree. I mean, I think it's the sort of now they're saying sort of line. Today milk is bad for you, and then in 2 weeks' time they're going to say milk is is good. So that's definitely the case, and I mean that's why I mean the commentary I wrote about dark chocolate, which the BMJ published. I said it's just remarkable that it's by the same group who did vitamin E and beta carotene, all of those things. Everyone that's been tested in a trial not matched, but they just carry on publishing them because they get press coverage or whatever. So there's a problem with journals as well as the people who need jobs and therefore submit papers. But yeah, and that's definitely the case. But I mean, one of the big, as I say, one of the great advantages of triangulation would be there'd be many less papers. I mean that would be the value of it. So yeah, so I agree with you. I mean, I in 1991 with Andrew Phillips looked at the story with HDL cholesterol, and we looked at the measurement difference, the measurement characteristic differences, and your HDL is absolutely stable. If you have a full English breakfast, your VLDL, your triglycerides, etc., remnant cholesterol, increases dramatically. And I used to take some blood from in the Caerphilly study, and the guys who had had 4 or 5 pints of Guinness the night before, you know, when the supernatant was cloudy. You know, you could see the triglycerides. So we just said, well, surely there's just more measurement, so much more measurement error in triglycerides, and they correlate so strongly. If you took measurement error into account, it's about minus 0.8 or 9. That, you know, the evidence is really unsecure on HDL, and then started applying the same. I was actually registered to do a PhD on fibrinogen mediating job stress to coronary heart disease, and I then applied the same approach with measurement error, and I realized this question is just absolutely unanswerable. You couldn't get an answer that was believable. So I went off and worked on things like HIV, because it wasn't a causal issue, it was actually doing interventions that might do some good. I mean, I think a large amount of the literature is just completely ignored because it's just meaningless.
George,
I don't think that's true, by the way, just of epidemiology. I just think I mean, because epidemiology introduces sort of menaces of everyday life, people are interested in it. I mean, that's why the papers publish it, because everyone has to eat, so you're interested in those stories.
George, that was a great talk. Austin Hill is criteria related to smoking because of smoking.
Yeah.
I think the trials have not shown anything, or if anything, not adverse outcomes. So the question for you is, how much evidence, given that it's all imperfect, do we need to act? Whether it's plan to change, all the evidence is imperfect. At what point do we act on imperfect evidence?
Yeah, no, that's a very good question. And I mean, one answer about the trials is, this is of interest to Katie, because it was a trial that Jeffrey Rose and Patrick Hamilton did. It's the only single factor smoking cessation trial there was, and didn't show any, you know, it was much too small, and it didn't show any benefit. And in fact, even though we've not really should publish it, Martin Shippey and I looked at the when they did the 30-year follow-up of Whitehall 1, and you could get the trial men out of it, and of the survivors, there was no difference in there had never really been any difference in the smoking. They just reported they weren't smoking, but 20 years later, when they were looking back, they were. So there haven't been. There's only the lung health study did get a sort of bit of a difference in smoking, but you're right. The randomised trial data are absolutely. They're just not there for smoking, but the evidence. But I mean, I think that's why all of these questions, all of these pointers, I think point to that. I mean, the issue is to what extent. I guess the issue with triangulation is actually just trying to formalize it, and then trying to come up with ways of actually combining the evidence. So so I mean, I in the end, it's a question for policymakers, clearly, and it's something that's contested. I mean, I'm worried with the willingness to start admitting real world evidence into drug licensing opinions. I mean, the people, the FDA are talking about that as one might imagine, and I know everyone knows about the paracetamol thing from Trump, but he also advocated use of this this folate mimicking drug with tiny amount. The evidence is basically virtually non-existent, but that's going to be licensed, on the grounds of weak evidence. So so ultimately it's a sort of political.
It's a bit dispiriting, George, isn't it? I mean, when do we believe the observational data? When can we believe even RCT data if smoking cessation shown not to work?
Well, yeah. I mean, there's just no trials that actually got big enough got a difference in the smoking
And a
split.
lot of people do reference use of real world evidence to support biomarker development, for example.
Yeah.
You know, we've just run a trial of a biomarker that took 10 years to develop and that took 6 years to run the trial. The trial turned out to be negative. The point about observational data doesn't always play expertise, but if you're on a 6-year, 16-year cycle for turning these things around, the world has moved on by the time you get to demonstrate the potential benefit or otherwise of your biomarker.
I think certainly in the pharmaceutical industry, would not now run trials of things like HDL cholesterol without taking account of the genetic data, for example. They just wouldn't happen if you didn't have the genetic support.
Stephen?
So this question relates to a previous one about the kind of inverse relationship between the visibility of science publicly and the reliability. Often it struck yesterday by an email which I pinged on and showed me the list of the world's top cited scientists, among which you are very prominent, but not the top cited scientists in the world. But the person is a nutritional epidemiologist, and I wondered, you know, we obviously that work is cited extensively. Does citation drop off when things are proven to be wrong, or do they actually increase? I just wonder what the driver of the extraordinary citation rates of some of these individuals.
So the world's highest cited scientist is the person who is behind the vitamin E trials, the folate, the vitamin E, not the trials, the person who was behind those studies. I mean, but they carry on producing the citations for those. Yeah, those vitamin E papers aren't. I'm about the only person who ever references them now. You know, because but they move on to other things. Citations do eventually go down with things which are shown to be fallacious. But there's very little promotion there's just no promotion of null results. I mean, you're not going to be getting a press release on your trial, are you?
Well, no, we struggled with it. Yeah.
So I mean, that's the. I mean, and that's one of the things that the gold, recreating gold standard science. The official stuff from the NIH is null results are as valuable as positive results, which is true. I mean, null results stop. Things that stop things can be the most impactful science would have been to stop trials that waste money and are unethical to do trials that in the end aren't likely to help people.
Question at the back. Put your hand up. Oh, it was you.
I was very taken by that little story you just gave about not continuing with fibrinogen. Very wise, an unstable thing that happens when all kinds of acute events occur. And instead you chose something which had a bit more chance of running for you. What advice would you give to a young clinical epidemiologist about the track to take now?
Yeah, no, that's a very good question. I mean, one always has the personal biases of what one's interested in, and I do think that formulating ways of putting data together, but in particular for identifying what crucial pieces of evidence are necessary, but in answerable questions. So one is to look at answerable questions. I think questions in nutrition are almost unanswerable by epidemiological approaches. You just can't quantify exposures when they're so variable over time and between people, etc. I'd think about answerable questions and to always spend time on looking at what's known about things. There's a huge amount of sort of circular that sort of ties into Patrick's question. There's a huge amount of sort of circular epidemiology, which is just doing the same thing, showing things that have been, which are definitely true, smoking and lung function, etc., showing them again and again and again when there's just absolutely no value in that. What they're going to show. So, I think the thing you'd have to be excited in what you're looking at.
Can I just ask one last question, maybe? I'm minded that 20 years ago, the genetics community found itself in a similar world, that there was about to be an explosion of genetics data. There was a load of publications coming out which nobody knew how to make head or tail.
Yeah.
And they came out with some really clear rules that really helped the field to move on. Do you think, I mean, we're on the cusp of an explosion of data and presumably therefore correlations with healthcare outcomes and all sorts of other bits and pieces. Is there a chance that the clinical epidemiology community is going to come out with a set of rules that unless you meet these criteria, your publication's not going to get through?
So, well, so the great thing about with genetics is that it's randomized data. So it's one of the few situations where where p-values actually mean something, because you actually know that you're looking at randomized data. So it was sort of easy, introducing genome-wide significance as a requirement. Got rid of all, as you know, all the vast majority of these candidate gene studies just weren't true. And disappeared when that was introduced. I mean, I obviously would think that journals, it should be up to journals, funders, etc. I mean, funders did change with trials. You couldn't apply for a trial unless you had done a systematic review to show what trials had been done so far and put those data together. I think for funding and for publication, the same criteria should apply. You've got to actually say what's known about a topic, and what actually those studies add.
Very good. I think we should move on, but thank you very much, George, for a fantastic